Welcome to the first lecture video of our Class 19 series of lecture videos. In this video, we're going to be switching gears. We're going to discuss retrosynthesis. And so, what is retrosynthesis? It is the process of thinking about how you make a complex molecule from reactions that you've studied before and simpler molecules that complex molecule might come from based on your knowledge of those reactions. So as the notes say, we use basic reactions and reagents in synthesis. And let's take an example. Let's take methyl tert-butyl ether. So this is an oxygenated fuel additive that is still used in some gasolines. How might we think about making this molecule? Well, you might think about putting it together from a couple of radicals, maybe a tert-butoxy radical and a methyl radical. This is not really convenient types of reagents. We haven't really studied radical reactions that led us to believe that it would be simple to form oxygen-carbon bonds through those types of radical reactions. How about we break the oxygen-methyl bond, giving both electrons to methyl. So we use a methyl carbanion, and we have this tert-butyl oxonium cation. Well, a positive charge on oxygen isn't really easy to make. We haven't really tried to put things together in this particular way. But what if we put the two electrons in that oxygen-carbon bond of the oxygen-methyl bond of our MTBE onto oxygen? So we have a tert-butoxide, and then we would need a methyl carbocation type of reagent. Well, I could think of corresponding reagents that would give us this, and I lost my G. Corresponding reagents. So retrosynthetic analysis is a thought process. You can tailor specifics in the forward direction, and basically we like to draw these backward arrows to simpler things that we know we could actually have and use at our fingertips. So why don't we do that? So for example, I could get sodium tert-butoxide from tert-butyl alcohol and sodium hydride or some other base capable of deprotonating my tert-butanol. I could get methyl bromide from methane and bromine through a radical reaction. And then if I mix these things together, my methyl bromide is really my source of carbon electrophile. I would do an SN2 reaction, and I would get my methyl tert-butyl ether and sodium bromide through an SN2 reaction. So we can envision routes to tert-butoxide from simpler hydrocarbons. I think we might remember that if we took 2-methylpropane and we did a radical bromination, we would be selective for the tertiary hydrogen on that compound versus the primary hydrogens in terms of abstracting and adding a bromine. And then, of course, we could throw that in water and we would get our tert-butanol as the major SN1 product. We might get a little E1 byproduct of 2-methylpropene, but not something we would really worry about. Throw in some sodium hydride, we lose hydrogen gas, and we get our sodium tert-butoxide. Or we could go other ways. We could get a tert-butoxide from the reaction of a Grignard with acetone. We could get acetone from isopropyl alcohol. We could get isopropyl alcohol from the reaction of a Grignard or an alkyl lithium like methyl lithium with acetaldehyde. We could get acetaldehyde from the oxidation of ethanol with PCC. We get ethanol from what? Methyl magnesium bromide and formaldehyde. Remember, formaldehyde is a good way to extend a Grignard's alkyl component by a CH2OH after aqueous acidic workup. And then we could track back our methyl magnesium bromide to methyl bromide, which could come from methane and bromine. So, you can use all the reactions that we've learned so far and think back to much simpler molecules. Of course, no organic chemist would actually go all the way back to methane and brominate it. We would probably buy methyl magnesium bromide. We would probably buy acetone so we could forego all this time and energy. But yeah, if you're stuck on a desert island and all you have are simple reagents, yeah, I guess you're stuck moving forward with those simple reagents. So based on this backwards direction, you can see how complicated the forward direction would look. So here we go in a forward direction. We take methane, throw in bromine, do a radical reaction to methyl bromide. We could make our alkyl lithiums by adding lithium to that. We could make our methyl magnesium bromide Grignard by adding magnesium to methyl bromide. We could add in sodium hydroxide, do an SN2 reaction, make methanol, throw in PCC. No water, we generate our formaldehyde gas. Take your formaldehyde, add your methyl magnesium bromide, followed by aqueous acidic workup. You have ethanol, add PCC, no water. You have acetaldehyde, add methyl lithium, followed by aqueous acidic workup. You have isopropyl alcohol, PCC, no water. We give you acetone, add methyl lithium, and you have now lithium tert butoxide, and throw in methyl bromide, and you've got your MTBE, right? It would be very difficult for you to think forward in this manner to get to MTBE. That's why we use that retrosynthetic analysis to go through all these steps to get to our simpler reagent like formaldehyde and methyl bromide, which comes from methane, right? So retrosynthesis, that's how we use it. Of course, when I did this as an in-person class, I would only give points for a forward direction, and typically I would ask that students, show me what the product is after every 2 or so steps. So not to have, build up 8 different steps. In this course, of course, we'll be looking at multiple choice problems, and I'm sure I will have some, options that, have proposed synthetic routes that would stop after a couple of steps, and you'll have to evaluate whether those are reasonable products and reactions that have been proposed and select, the best possible one. So it would be useful if you were familiar with retrosynthetic analysis so you could check and make sure, I've done a good job in presenting various options. So that pretty much finishes our first video for this class time series. Good luck with the problem, and I'll see you in the next.